Bark, 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 bark. Because we're talking about work. So we are in a new unit now. Unit 8 is all about work, and as we will see eventually, it's also a little bit about energy. This video that we're going to do here today is a lot of the introduction into work. It'll show you a little bit of new mathematics that you might not have seen before, as well as just kind of covering the general idea of what are we actually talking about in the world of physics when we bring about the word work. Because it's a little different of, you going to work or what does it mean for you to actually do work? That's what we're going to discuss right now. So let's do it. So first, what is work from a physics description? Well, in the world of physics, we think that work is done. It is something that you can physically do. It is a process. This is unlike a property like mass or a length. For instance, if I take a look at this Xbox controller here, this Xbox controller has a mass, and therefore it has a weight, mass times gravity. It has some width here and a height and a depth associated to it. If I licked it, it would have a taste. Probably not tasting anything good because it's just plastic, but those are properties that this controller has. Work is not a property. You do work. Do work, son, right? So you do work. It is done. And it has to be done on something. So work is done on an object. You can't just say, like, I'm doing work. Well, what are you doing work on? Because that is the physics definition of doing work. So you can pick a brick, an electron, a truck, a beehive, whatever you choose. But you have to do work on an object. So far we have that work is done on an object. And this work that is done on an object is done by a force. So we have to have a force acting on an object in order to do work, okay? We could either do this for one specific force, or we could have a net force, a sum of forces, to look at the net work amount that is done. Now, this is kind of weird, though. When we think about doing work from a physics perspective, that force, which is either pushing or pulling on an object, it has to cause the object to be displaced. It has to cause the object to move. If you are pushing a wall and that wall is not moving, it does not matter how hard you are pushing it, you are not doing work. There is no displacement on that wall. If you push the high school and it doesn't move, you haven't done work. You might be getting tired. You might be, spending internal energy as your calories are burning for your body, but you're not actually doing physical work. So kind of weird thing. We'll see more examples of kind of weird ways to do or not do work throughout this video. Okay, but that is our definition. Work is done on an object by a force when it affects the object's displacement. So when the force affects the object's displacement, that is doing work. Now, that's like the nice English definition. How do we do it with math? So this is kind of weird, but it bears mentioning. Do you remember back in maybe second or third grade, you learned how to multiply? And your teacher was like, when we take 3 times 2, times means to multiply. 3 times 2, we wrote it with that x, right? That x right there was multiply. And we said 3 times 2 equals 6. And then a few years later, maybe 5th or 6th grade, they were like, oh, only babies use the x to multiply. We're big kids now. We're going to use the dot. When you see a dot, that means multiply. And you're like, oh, okay, yeah, great. We're not babies anymore. We can multiply with a dot. That's so cool. And then a few years later, they were like, why are you using the dot? Anytime we want to multiply, we just put everything in parentheses. And this is why I'm always super paranoid about my parentheses, because parentheses are how you multiply. So those are all different ways to multiply, right? Well, as it turns out, this x and this dot here, that is not just multiplication. That is a special type of multiplication, and it is specifically reserved for vector multiplication. When you did multiplication earlier on in your careers, you were always technically acting in just one kind of direction. You'd go 1, 2, 3, 4. I went 1, 2, and if I do it again, 3, 4, and if I do it again, 5, 6. That was one direction there. What we are going to do is instead of multiplying scalars together, what happens when you multiply vectors together? We know that force is a vector. It has a magnitude and a direction. We know that a displacement, what we've called delta x throughout the year, but we could just call x for now, these displacements are a vector in and of themselves. And because of this, we cannot just multiply things together like 3 times 2. This goes into a similar idea how earlier on the year we said, like, what's 3 plus 4? And then, everybody answers 7. And that's true, except if you go up 3 and over 4, well, that resultant vector is 5. 3 plus 4 is 5. That's because we're adding vectors. Multiplying is just as weird for vectors. We have to have new terms of multiplication, and the methods we use for that are a cross, the x, or a dot, the dot. So we are going to be using the dot product in this case for work. That is what we use here. And the dot product, also known as the scalar product, because it just gives us back a scalar, some number, is the multiplying or the multiplication of a force and a displacement. And the weird thing about this is whenever we write these dot products, you're multiplying two vectors. So here's vector A dotted with vector B. And we would literally say here that this is A dot B. Sounds kind of weird, but that's what it is. And A dot B is going to give us a scalar or just some number, which is D here. So that's just some quantity. Now what we're trying to do here is we're trying to say how much of vector A is parallel to this vector B, or vice versa. I like to think it easier as vector A being parallel to vector B, and we'll see a demo of that in a second. When we actually build this out, though, and get our scalar answer, okay, some given amount, for work when we do this, this value D here, this scalar here, that is going to be the work. And our two vectors, A dot B, are going to be F dot X. We can expand this so that this is going to read that work equals Fx cosine theta. In this case, the dot went away and it became the F cosine theta term here. So F dot X equals Fx cosine theta. Okay, that is what is going on there. That is what's happening. And we'll see just why that cosine magically appears all of a sudden just in a second. So one note is that this x that we have here, we are considering that to be the displacement. Instead of writing delta x everywhere, I'm just writing an x. Sometimes I'll write delta x's, sometimes I'll write x's. The thing to recognize is that these x's here are really displacements. They are vectors. Now for units, work has interesting units here. In the English, a force in English is a pound, and distances or displacements can be feet. So for English units, we actually get a foot-pound, which has got to be like the dumbest thing you've ever heard, right? Literally a foot-pound, like pound it, but with your feet? Nah, but that's what it is. It's a foot-pound. We'll also see that unit come back a little bit later on when we talk about torques. But in the SI units, or the metric units, we actually find that work is joules, and 1 joule equals a Newton meter. Newtons from forces, meters from displacements. But note, joules are also units of energy, which start to bring about the idea that this work that we might be doing has something to do with energy, which we'll see later on in this unit. Now, where did that cosine theta just magically come from? Well, here's a box, and it's being pulled with some rope at some angle. Okay, so there's a force here up at some angle, and because we're pulling on this box with some force at some angle, the box is going to move to the right. Now, if we took the dot product of this, we would want to find what component of the force is acting parallel to the displacement, parallel to this x. And the way we'd find that is we'd break up this force vector into its x components and its y components. And if you're like, how do you do that? Well, remember, even though this y component is drawn on the left side, you could complete the triangle here. And that's just SOHCAHTOA, right? So if we could use a SOHCAHTOA, then we could find Fy and Fx. Well, for the dot product, we are trying to figure out what component of this force is in the same direction or parallel to the displacement. So this Fx right here is parallel and it's in the same direction as this displacement here. So Fx is what we want. And what we can do here is we can recognize that this Fx is actually F cosine of theta. If we use the cosine of SOHCAHTOA, we find that this Fx, this adjacent side here, is F cosine of theta. Which means if we take F cosine theta and multiply it by the x value, the displacement here, we just get Fx cosine theta. This is the component of the force vector that is causing the object to move. So that is what is causing the work. The y component here, that's not causing this object to move left and right. As we saw back when we looked at forces in Unit 6, that y component is just alleviating some of the normal force here because it's kind of pulling up. But the x component, F cosine theta, is what's causing this to move to the right. So what we see here is work equals F dot x, which equals the parallel component of the force to this displacement vector. That equals F cosine theta times x, which is just Fx cosine theta. And these are all just multiplied together whenever you have those values right at the very end. It's a very nice way to set that up. Now, when we take a look at some examples here, there are a number of instances when you could do zero work on an object. And this is kind of a weird idea, like I said before, but you can actually do no work even though it feels like you should be. So you could do no work on an object if that object is not moving, if there's no displacement. In this case, like you're pushing a wall. The wall's not moving even though you're exerting a force on it, so no work is done. Or if you're holding a really heavy object above your head, like let's say you're bench pressing and you bench press up and you hold it there, it's difficult to hold it there. You're exerting some force, but this isn't moving. Once it is held there, it is not moving anymore. And because of that, there's now no displacement. The act of bringing the object up, that is some amount of work. But once you hold it there, you're not doing anything. There's a force, but there's no displacement once it reached this location. So in those examples, zero work has been done. You can also do zero work if no amount of force is acting on the object, or a net force is not acting on an object. For instance, if we take a bowling ball, so this is a rolling ball with no friction, and a bowling ball is a rolling ball on a very well waxed and buffed floor, right? So if there's no friction here, once this ball starts moving, it has a velocity, and because of that, it goes some displacement. But once that bowling ball leaves your hand, there's no force acting on the bowling ball. It's gone. It's just doing its thing. Remember, a velocity is not a force. Forces are active pushes and pulls. Once you give an object a velocity, it will have that velocity until some outside force acts on it, okay? So there is a displacement here. The object is moving, but there's no force acting on this object. So there's no work done as this object's moving. Kind of a weird idea. We also get zero work even if there's a force and the object is moving, has a displacement. In this case, the cosine theta term is what causes zero work to be done. Remember, if theta is 90 degrees, cosine of 90 degrees on the unit circle actually equals 0. So, in certain situations, the force and the displacement could be perpendicular to one another, causing for no work to be done. One example of this is actually a satellite in orbit. We talked about this in circular motion briefly. We'll talk about satellites and orbiting planets later on in our gravitational unit. But for a satellite to go in orbit as it goes around a planet, there has to be an inward acting force on the object. So there's an inward acting or a centripetal force pointing towards the Earth here. But the comet or the satellite here is moving to the right. So its displacement vector is to the right. Well, if the force and displacement vector due to the velocity are perpendicular, well, that cosine of 90 is now going to be 0. So that angle there is 90 degrees. We know that's going to be a 0. If you're holding an object, like you're walking a 2x8 around, or you're holding those weights again, right? Or maybe you're bringing in a lot of milk from the grocery store, and naturally, because you're a strong individual, you have to carry it all in one trip. Well, whenever you're holding something, your force is acting upwards, but you're using your legs to move yourself left and right. This means that this force and displacement are perpendicular to one another. The angle's 90 degrees. And like we said, since this is work equals fx cosine of theta, cosine of 90 by definition is 0, and anything multiplied by 0 is going to give us 0. So in this case, there's no work being done. So a lot of weird scenarios there to have no work being done, but that is how we define it. You can also have negative work being done. While work is a scalar, so it's just a number, it doesn't have a direction, but it can be negative because you can put work into a system or take work out of a system. If you have friction slowing a box, so maybe a box was already moving to the right, friction's going to oppose that motion, and friction's going to act to the left. The angle between these is 180 degrees, and that means when you run fx cosine of 180, the cosine of 180 degrees is -1. So you get a negative work in that regard. A similar thing happens if you're walking your dog. My favorite name for a dog is Socks, by the way, if it has white feet and a black body. But if you're walking a dog, maybe that dog wants to race down the street and wants to go to the right. You are pulling back on the leash back to the left. Now, while this angle here isn't the full 180, it is greater than 90 degrees. And any angle greater than 90 degrees is going to cause that cosine component, or that cosine value, to become negative. So any angle greater than 90 degrees, we get a negative value for the cosine, and that is going between 0 and 180. If you go around far enough, the cosine becomes positive again, but all of our angles be 0 and 180. So we get a negative value here. So to reiterate, we're looking for a parallel component of force. If that component of the force is acting in the same direction as the displacement, we get a positive work. That force is helping the object move. If your force is perpendicular to the displacement, then this force isn't helping, you get 0 work. And if our force is acting against the object's displacement, we still only want the component of that, so we're still going to have this cosine term, but that amount of work will be negative. So that's what we're looking at when we're talking about work in the units of physics, okay? The next thing we're going to talk about in future videos is the idea of power. But for right now, we're just going to take a look at work. And then coming up, we're going to see a few more videos on how to actually get these angles, how to look at problems, and how to calculate some work quantities. But until then, until we look at power together, adios and take it easy.